let's go ahead and work on our last three methods. So let's do the two easy ones first. Get and set. Public get not item, int index. So given an index, I wanted to retrieve something from that index. Fairly straightforward. Minimally, we could just do this. Simply says remove a return list index, but if we wanted to be safe, we would want to check to make sure that that wasn't going out of bounds. And the reason is that, yeah, if it was out of bounds, this would print out an error. This would give an error, but it would be an array out of bounds exception. We want a more general exception. So if, or rather more specific to our circumstances. So if the index is less than 0, what we had earlier, but now, and by the way, it's an or, not an and. That you might get confused there, right? But it's one or the other. If the index is less than 0, or the index is greater than or equal to size, not greater than size, but greater than or equal to. Why? Because while size is a valid index to add to, you can add to any index from 0 to size. You can't retrieve an item that doesn't exist yet. You can add to the very end at that last location that doesn't exist, but you can't retrieve anything there. So the only valid locations, just like in an array, that you can grab are index 0 to the size -1. So, hence the greater than or equal to size. So, if that's the case, then we can just simply copy this exception over here. And that's done. Similarly for set, I can just copy this sucker over here because set will also return an E. It will take in an index and it will return and it also takes in an item that we are going to replacing the item at that specific index with. We want to return the old item though. To list. So we grab, first thing we do, check for the index, then we grab the old item out, put in the new item, right? With the set, we're just replacing an item. So we retrieve the old item, put in the new item, and then for this final step, what are we going to do? We are going to put in list. We are going to return old item, the item that we just removed, so that the user has the option of doing something with it, right? That took 3 minutes, so that's why I just wanted to do them together. So let's go ahead and go into the remove method. The remove method is an easier version of the add method. So public remove, we're going to return the item we're removing just like we returned the item we're replacing with set. We're also going to do int index over here as opposed to the other remove method, which is the one that returns a Boolean that says given a specific item I'd like to remove that. We are going to remove int index. Okay. We are going to return null over here for just a second so that we can quash that error. And now let's go ahead and center this a bit more. And the same exception over here I'm going to copy because it's the same thing. First thing I need to do is check, is the index less than 0 or is it greater than or equal to the size? Is it an actual index I can remove something from? If not, I need to yell at the user and, well, you don't want to call them an idiot because programming is tough enough as it is without the computer insulting you. So, next thing I want to do is go ahead and retrieve the item. Whoops. Go ahead and retrieve the item that I am removing. So, to return. You can call it to return. You can call it old item, so long as it's a meaningful name that helps encompass what its role is. To return is equal to list index. So we retrieve that item. We can retrieve that item safely because we know it's at a valid index. To return over here. Next thing we need to do, though, is that once we remove an item, right, let's go ahead and just once we remove an item, say we remove this 3 over here, what needs to happen is that in order to remove it, this 2 needs to come over, this 1 needs to come over, and this 0 needs to come over. And I almost forgot a very crucial step. When we remove an item, we got to remember to do size minus minus, just like we need to remember to do size plus plus. Okay, so what we need to do is remove that item. So let's go ahead and think. And let's go ahead and also work on a bit of an easier example. So let's just go ahead and add 20 items. Put this out at the end and just add them onto the end so you get 0 to 19. Okay, so there we go. So if we wanted to remove 3, 4, 5, 6, 4 needs to... So to remove 3, what do we want to do? We would take 4, we'd copy over to 3, take 5, copy it over to where 4 is, take 6, copy it over where 5. So basically, where I am, I'd want to grab the guy to the right of me and store him in my location until I get to the end. So how do I do that? Well, from here, rather than just going down, I'm going to go up the array. So I'm going to start... I'm going to start at the location I want to remove. So 4... Oh, and I'll do it after I've saved that item. So 4 int I is equal to 0. I is not 0, but I is index. And then it's going to be an I++ loop. And when is it going to run? It is going to run when we do. So it's going to run up until the point where it's going to run up until the end, right? We got to grab everything and move it down. Everything to the right needs to be moved down. So we're going to go up to size minus 1 because this item, right, will grab the last item. I is less than size minus 1 as opposed to size because we'll want to go up to the second to last item, grab the item to the right of it, the last item, move it down. If we went up to size instead, we'd be going up to here, trying to grab the right item, which doesn't exist, and we'd get an error. So what we have to do over here is say list I. At my current location, I want to store list of I plus 1. In other words, I want to grab the thing to the right of me, get stored at my location. Right? If you notice, it's actually the reverse of how the add method works, which is convenient. So let's go ahead and test our final method. So what I'm going to do is that I'm going to remove index 4 each time. So 4 my fingers are just disagreeing with me. 4I is equal to 0. Do this 5 times. List.remove index 4. So now if we run this, well, it's not going to look like we did anything because we didn't print out, because we should print out every time we remove. And there we go. 1, 2, 3, 4, 5. So here we remove index 4. Remove index 4 again. Then what's in index 4? What's in index 4? We can also remove the first item. We can try removing index 0 a bunch of times. Let's do that. And that works out. We can also try removing index I, which will remove which will remove 0, then it'll remove the 2, it'll remove the 0, then it'll remove the 2, then it'll remove the 4, then the 6, then the 8, and we're done. So those are all the methods for add and remove. And this is essentially how you use an array list. This is how an array list works. Now, you might be saying, wait a second, aren't we missing something? What about reallocate, right? Add how to reallocate. If remove is a mirror of of that? Shouldn't it have a reallocate? And that gets into a very interesting point, right? Suppose that basically that we would reallocate when there were half the items of the capacity to shrink it down. Well, suppose that basically we had 1 million items, right? And the capacity was 1 million, right? And now we add 1 item more, so we double our capacity to 2 million. So we've got 1,000,001 items. Capacity 2 million. Current unused space 999,999. So now suppose we remove an item and that we reallocate. Then we remove another item. Sorry, we don't reallocate that first one. Now that we remove a second item, remove 2 items from that 1,000,001 at a capacity of 2 million. Filled up. Sorry, we're at half capacity, so we shrink back down to 1 million. So we create a new array of size 1 million, copying everything over. 999,999 items. Wasted space 1. But then we add 2. We add 2 more items to the end, and so we reallocate again. And we just keep and now just imagine a situation where we keep doing that again and again and again and again and again and again and again. Which can happen if you're really unlucky. And that's super inefficient because that takes time. Time being a discussion for the next module. The amount of effort that takes. So, what am I going to do? The thing to do in that case is that we have 2 different ways of handling it. The first is don't reallocate when we don't shrink to reallocate. Just reallocate when you add items, and if we make space, we make space. The second approach is that is rather than shrinking when we're at half the capacity, shrink when we're at a quarter of the capacity. That way you avoid that particular loop of allocating, reallocating, expanding, reallocating, shrinking. But that reallocation takes time. It's quick to add something to the end because we don't have to move any items over. But adding an item to the end, we just stick it on. Getting and setting, that's really quick too. But what do I mean by quick? And what do I mean by inefficient and slow? That's the topic of our next module. So go ahead and work on this homework, but the next module is waiting for you.